So again, thank you all for joining. As Lily said, my name's Charlie Penny. I work for Senior Flexonics, and I'm the coordinator for HEATSTACK, and Kun Zhang is from the University of Birmingham PhD project, and he's been doing the work on the material of choice. The other partners are Sunfire, who manufacture the stack, and they took over from Violent in 2017, and they're now actually manufacturing the whole micro CHP module. So they're both the stack and the module manufacturer. We also worked with Ichicalde in Italy, who again used our heat exchanger with their PEM fuel cell for processing or recovering heat from their exhaust gas. But what Kun and I will talk about today is things just directly related to the work which Senior Flexonics and University of Birmingham have done. So the objective of HEATSTACK was to aid in making micro CHP fuel cell systems more cost effective. This will help us to reduce CO2 emissions by introducing the fuel cell micro CHP, reduce NOx, decentralize supply of electricity, and improve efficiency. So the two main ways of doing that were to improve the manufacturing process, which would improve quality and reduce time to manufacture. Pretty obvious. And the other way was to actually, by improving quality and improving processes, improve the durability of the overall system, so the system life was increased, which again is a reduction in cost. The solid oxide fuel cell stack requires a cathode air preheater. So the cathode air preheater, as the name suggests, preheats the air going into the solid oxide fuel cell stack. This significantly improves the efficiency, enables the fuel cell to function its working temperature. So before HEATSTACK started, we had been supplying Violent, who were the early partner in HEATSTACK before Sunfire took over all of their activities. There. And can you all see my screen?
Yes, yeah, I can.
Yeah, good.
Yes.
Okay. So as I was saying, before HEATSTACK started, we were supplying Violent with heat exchange plates made from Inconel 625. 625 contains around 60% nickel, so it has very good high temperature strength, which is suited to the working conditions of the cathode air preheater. Gas inlet temperature typically around 800 degrees C, but it has two major disadvantages. The nickel, of course, is very expensive, and so it makes 625 expensive. And the corrosion resistance layer on 625 is a chromium oxide, and at high temperatures the chromium oxide can evaporate, and the chromium then contaminates both the fuel cell and the waste condensate. So working with Violent at the time, at the start of HEATSTACK, it was decided that we needed to change the material away from 625. We did initially try a different AluChrom with a higher percentage of aluminium, but that was almost impossible to work with. So we went for AluChrom 318, which has 3.5% aluminium, which is just above the minimum amount of aluminium content to ensure that the surface regenerates. Very low nickel content. So with this large reduction in nickel content, we have the potential for significant cost reduction, and because we have an alumina surface on the material, not a chromium oxide, then the chromium evaporation is much reduced, and Kun will talk about this activity that the University of Birmingham did. So this is the image of the cathode air preheater for HEATSTACK. So we had gas in here coming from the exhaust from the stack and the tail burner, flowing between the cells and out through here, and then air flowing in through this tube, contraflow with the gas, and out through a tube opposite this. So it's quite a compact, relatively lightweight system. So the plates are 0.3 millimeters thick. So it is, and because of its construction, we actually allow the whole system to move and distort as it wishes. And both Violent and Sunfire have shown that it has minimal effect. The distortion has minimal effect on the life of the component, or the performance of the component, I should say. So, as I said on sheet 3, the low percentage of nickel in the AluChrome 318 has a potential to significantly reduce the cost of the cathode air preheater. The difficulty we got in the immediate is that 318 is a new material and it hasn't got a significant market. And until we can start to develop the market, both with our own products and the VDM can sell 318 to more customers, we're not really going to see the advantages of the cost reduction. So, you know, part of HEATSTACK is actually to try and highlight the advantages of AluChrome 318, so that even our competitors come in and use it, because then it will help the whole industry to reduce costs. So we wanted to help VDM to market their material. Of course, a further cost saving with the 318 is reduced chromium evaporation, and with less chromium evaporation, there's less contamination of the stack, which gives it increased life and reduced overall cost. And also, because we're not contaminating the exhaust gas, which then forms condensate when further cooled, it allows us, or allows Sunfire, to reduce the size of the filters or have longer life filters. So again, a cost saving. So it's a significant advantage with the use of AluChrome. As we discussed, Inconel has very good properties. It has elongation of 51%, which means it can be easily formed. AluChrome 318 has only 22%, which means that it cannot be formed into such deep or rapid cross-sectional changes. So we needed to do quite a lot of work to get a design which both met performance and was formable. And I'll show you images of some of the problems we ran into on the next sheet. But with working with Violent at this stage, we were able to achieve a cathode air preheater with the same performance as the 625 formed cathode air preheater, but with a very much changed profile. The other problem we found with AluChrome almost straight away was with the 625, we could nickel braze it, which meant that when we were laser welding, if we had a small leak, we could put a dab of nickel braze over the leak, vacuum braze it and repair it. We tried many different things for brazing the AluChrome, all were unsuccessful. So that meant that we had to very much improve the quality of our laser welding. And that's where HEATSTACK came in, because it allowed us to manufacture new tools, try new things, and develop our welding parameters. So that was again successfully achieved. So you can see on these images here, when we were first forming the AluChrom, we were getting splits in many places. And what we had to do was reduce radii, reduce material elongation, so that would reduce the thinning and stop the splitting. So we had a few iterations to get this correct. And of course, you can't only think about the forming, you have to make sure that the performance is maintained as well. But since we've done our trials, we haven't had any problems with splitting plates. Here we can see what the pre-HEATSTACK plate looked like and what it looks like with the AluChrom for HEATSTACK. We also picked up cracking in the weld on the AluChrom initially, so you can see here we're actually cracking in the middle of the weld and sometimes cracking right through the weld. So again, that's all down to tooling and parameters to alleviate that problem. But once we developed that, we had no concerns with that, and had a very high, I think it's 97% right first time when we were laser welding these together. So if I pass you to Kun for 2 sheets.
Okay. Hi guys. My name is Kun Zhang, and as Charlie said, I'm a PhD student from University of Birmingham. And I'm responsible for the work package 4 of HEATSTACK project, which is material testing and analysis. So during the early stage of HEATSTACK project, the main task of work package 4 is to evaluate the corneal vibration of 4 different high temperature alloys used for cathode active heater. So the alloy we tested are Inconnect 625, stainless steel 309, aluminized 309, and AluChrom 318. So after the experimental evaluation, we selected the best material with the lowest corneal vibration for developing cathode active heater. So the corneal evaporation test was the corneal evaporation test of these alloys was conducted by the denuder technique, which was created by Chalmers University in Sweden. So in this slide, we can see in figure A is accumulated corneal vibration of.
Sorry, we cannot see your screen, so let me just make you a presenter because you didn't mention you're showing a presentation now. Just a second.
Okay, yeah, no problem.
Yeah, so now.
So yeah, so in figure A, we can see figure is accumulated corneal vibration of the 4 different alloys tested for 168 hours. So figure B is the corneal vibration rate of the 4 different alloys. So as we can see, Inconnect 625 has the highest amount of corneal vibration because Inconnect 625 produce pure corneal oxide as a protective layer during high temperature exposure. For 309, when stainless steel 309 exposed to high temperature environment, it produces corneal manganese spinel layer on the surface, which has a lower corneal version compared to Inconnect 625. Aluminized 309 and AluChrom 318 has the lowest amount of corneal vibration because of the formation of an aluminum layer on both steel surface. However, if we look into figure B, we can see the corneal evaporation rate of alumina 309 increased with time because during high temperature exposure, the alumina scale formed on the aluminized 309 surface suffered very bad scale sporulation, which exposed corneal oxide to the high temperature environment, leading to high corneal vibration. However, for for AluChrom 8, the chromium evaporation rate decreased with time, which means that the alumina scale formed on 8 surface had no scale sporulation and can also reduce chromium evaporation effectively. So based on the experimental results from the technique, AluChrom 8 meets the material requirement for developing cathode applicator for HEATSTACK project. However, after we tested the AluChrom 8 heat exchanger in SFC condition, we also found some other issues. Since the exhaust gas from fuel cell stack and the fresh air go into cathode applicator in opposite direction, so the hot zone and the cold zone will have different oxidation status. Here I have a figure to show you guys. Yeah, this figure. So this part is hot zone and this part is cold zone. So for hot zone, it produces alumina scale on both inner and outer surface of a single cell. However, for cold zone, it produces a large amount of chromium oxide on the outer surface of the single cell, and no oxide scale formed on the inner surface of single cell. So in order to optimize the material, so we came up with one idea, which is the pretreatment. And so the pretreatment will allow sufficient formation of alumina scale on the heat exchanger surface before we put it into real application. So the pretreatment was conducted with a different temperature from 800 degrees to 1100 degrees with different pretreat time from 1 hour to 4 hours. Different temperature will cause the formation of alumina with different phase. Like 800 degrees, it will form metastable alumina like gamma alumina. 1100 degrees will form alpha alumina on the steel surface. Compared to the metastable alumina, alpha alumina has the best chromium retention ability. So finally, we found the sample pre-treated at 1100 degrees for 1 hour has the best performance with 98% reduction of oxidation rate and 90% reduction of chromium vibration. So yeah, the photograph on the right side shows a single cell of AluChrom 8 heat exchanger after pre-treatment at 1100 degrees for 1 hour. So the color is different from the original plate because it covered with alumina on surface formed during pre-treatment. So next step, so we will put this pre-treated heat exchanger in real test. So there are two things we are expecting to see from the pre-treatment. The first one is no formation of chromium oxide in cold zone. The second one is decreased oxidation rate of alumina in hot zone. So okay, thanks guys, thanks for listening. Let's visit presentation to Charlie.
Thank you, Kun. Are you going to make me presenter, please, Lily?
Yes,
Lily?
sure. Yeah.
Yeah, can you give control to Charlie?
Yeah, I'm beginning.
So just to finish off what Kun was saying, so Kun proved that he could form an alpha alumina layer at 1100 degrees C in an hour, and that was done on a single plate. So then the concern for senior was, with that alumina layer, would it cause us problems with our laser welding? So then we did trials of laser welding the plates together to see what the effects were, and the results were very positive. So as we go forward, we'll be investigating with Sunfire on developing a pre-heat treated plate, such that the chromium evaporation is minimised straight from the off, and it's across the whole plate and not just the hot end. So it's been that was a very useful outcome which we weren't expecting at the start of the project, to show that a preheat treatment was very useful. So in terms of improvements in the manufacturing process, so when we started the HEATSTACK project and using prototype processes, it took us on average 8.8 hours to build one unit. HEATSTACK allowed us to buy capital and tooling to develop our production processes, and through HEATSTACK we've now reduced the time to produce a unit to 2.8 hours. We've then transferred all the capital and tooling to our manufacturing site in the Czech Republic, all ready for low volume production. And once the production engineers in senior Czech start working with the system, they will further improve the processes and reduce cycle times. So we will see a good increase in productivity from that. So senior now ready to deliver on our goal of low cost components for the solid oxide fuel cell micro CHP. HEATSTACK has delivered what it set out to do, and a very good funding from the EU for all the partners concerned. So it's been very pleased with the process. So if I look now, so this is our Czech Republic facility. They've just recently built an extension on their factory. So this is the laser welder here, and then they're just bringing the rest of the machinery in, and it'll all sit within this blue area and be the production cell. And just a quick one from Sunfire. We haven't put much there because they were unable to join the webinar, and I didn't have enough knowledge to really talk about it. But they've developed from a manual application of the glass sealant to an automated process with a 10% cost savings for the stack and improved quality. So again, Sunfire have been pleased with the results which have come out of HEATSTACK. So that's the end of the presentation. Kun and I will be more than happy to answer any questions that you guys would like to ask us. No, everybody's comfortable with that? Lily, can I pass it back to you?
Yeah, yes, Charlie.
Okay. Okay, well, thank you very much for listening in, guys, and
thank you so much for your time.
Yeah, thanks, guys.
Thank you. Bye.
And please feel free to contact either Kun or myself, and we will supply more information. Thank you. Bye-bye.
Thank you.
Bye.
Bye-bye.